Hello, welcome again to another tutorial video on the statistics part of this class. Today we want to look at the introduction to hypothesis testing, and hopefully at this point all of you have read the applicable chapters and have looked through the PowerPoint and all of the notes and are very familiar with the information contained therein. Today our purpose is to give you a video demonstration of how to calculate the statistical tests that are involved in this chapter. There are 3 separate ones, but they're all fairly simple, okay? And they are a progression where we do something slightly different with each test, okay? So we want to start off today with hypothesis testing for when we want to compare a single individual and their score to a known population. And so that known population has known parameters that, so we know the mean and the standard deviation for the population, okay? Whenever we know the mean and standard deviation for a population, and we want to compare a single person to that known mean and standard deviation, we use a basic z-test, the one that you guys are really familiar with, that you've been using ever since Math 1530 in your Prob and Stats class. But we want to look at that today with our in-class example and follow those 4 steps for hypothesis testing for comparing a single person to a known population value, okay? So our in-class problem reads, in a study to see if computer-assisted instruction helps children with reading difficulties learn reading skills better than average, an educational psychologist arranged for a child with reading difficulties to have access to a set of computer learning programs instead of the normal reading curriculum for 1 term. At the end of the term, he tested the child on a standardized reading ability test on which the mean for children with reading disabilities is 36 with a standard deviation of 6. If the test participants scored 47, would this provide support for using computer programs at a 0.05 level of significance? It sounded like I needed a computer-assisted instruction for children with reading difficulties just then, didn't it? But anyways, we want to follow the 4 steps of hypothesis testing for that. And so refer back to, your PowerPoint related to those other steps, but let's go ahead and set this up on the board, okay? I am comparing a single person whose score on that reading test was a 47, okay? So X equals 47. The raw score for that person is 47. The problem also said that the mean, let me check again, I'm 36, with a standard deviation of 6. So those are our known population values. And when we know the value for the population, it is not the mean and the SD, but rather it is mu and sigma. So refer back to your last section of information on descriptive statistics about the differences between statistics and parameters. But when we know the population values, those are parameters. So the mu for this population of children with reading disabilities is 36 with a standard deviation of 6, okay? And we want to use a 0.05 alpha level to test this hypothesis, okay? The very first step of hypothesis testing always is to state our hypotheses. And we need to state the null hypothesis and the alternative hypothesis. And what we are going to be comparing in this hypothesis is the score for that single person to the known population value of mu, okay? So those are the symbols that we find in our hypothesis. Now, whether there's an equal sign or a greater sign or a less than sign in our research hypothesis depends on what we're trying to figure out in our research. And our problem tells us we want to know if this causes this individual to score better. Would it provide support for using computer reading programs? Does that help the individual score better? So our hypothesis is that this person who used the computer-assisted instruction scored higher than the children with reading disabilities in general, okay? So our null hypothesis will always be everything opposite of our research hypothesis. So the null hypothesis is going to say no, it'll actually be less than or equal to the known population values. It's either going to have no effect at all, or it's going to have the opposite effect of what we are expecting. So they'll actually do worse, okay? The second step is to determine what the critical value for the Z statistic has to be in order for us to reject the null hypothesis. We set our alpha level at 0.05 in our problem, and we are doing a one-tailed test because we have a greater than sign, and also because that is a greater than sign, it is the Z-score we are looking for is going to be on the upper end of the Z-score distribution. So basically, I need to find the Z-score that marks the place on the distribution where 5% of people, or 0.05, proportion of the population scores above that point, okay? So in order to figure that out, I've got to go to my Z-score chart in Appendix B of our textbook, which starts on page 629 and goes through page 632. And I'm going to look at the area in the tail, beyond Z in the tail. See, it's beyond this Z-score in the tail of this distribution that is as close as it can be to 5%, okay? So I'm going to look on column C, area beyond Z in the tail, and I'm going to follow that column until it comes to 0.05. And I'm going to find that that Z-score actually could be one of two values. It could be 1.64 or 1.65, because both of those are equally distant. One is 0.0495 and the other is 0.0505, so they're exactly the same distance apart from that 0.05 range, okay? So we'll just stick with 1.65 because that makes for easier math, okay? So 1.65 is the Z-score that we have to have, we have to be greater than that in order for us to reject the null hypothesis and say that computer-assisted instruction did increase, significantly increase children's reading ability. So our critical value here is a positive value of Z of 1.65, okay? The next thing that we need to do is step 3 for hypothesis testing is to actually calculate the statistic. And the basic Z-score formula is that Z is going to be equal to that raw score minus the mean divided by the standard deviation, okay? So for our sample data, we end up with the raw score of 47 minus the mean of 36 divided by 6. So I end up with 11 divided by 6, which gives me an overall value of 1.83, repeating, I'm pretty sure, but let me go over here to my calculator and just check my math real quick, okay? So, calculator, 11 divided by 6, yeah, 1.83 repeating, okay? So the next step is to ask ourselves, is this value that we calculated greater than the critical value of 1.65 that we established was the cutoff for rejecting the null hypothesis? Is it more extreme then? Does it fall into this shaded region? So basically, is it a very rare score is what we're looking for? And we find that indeed, yes it is. 1.83 is greater than, which is what we were looking for, 1.65. And so based on that, we would reject the null hypothesis that there is no difference between that individual and other people with reading disabilities. Instead, that provides support for us that we would, that computer-assisted instruction does significantly improve reading ability in children with reading disabilities. So we do indeed reject the null. And in all of my classes, if you ever have me in class, we call it the hoe. That has come down from generations of psychology professors here at ETSU, including my professor way back in the day. But we are going to reject that poor hoe this time, okay? Always a good idea, actually, to reject the hoes. All right, and that concludes the the t-test for a single individual, okay? Now, most of the time, I'm not comparing one person to a known population. Most of the time, I'm going to have a sample of people that I measure, okay? And when I'm comparing a sample of people, I can't compare an overall mean for a sample to just a population of individuals. And this distribution would be a population of single individual people, okay? Instead, I have to create what is called a distribution of the mean in order to have a correct comparison distribution, okay? So think about it this way, let's come over here for just a second and just talk about some theoretical things here that you should have gone from the notes, but just in case. Let's say, I know in the population that IQ is normally distributed with a mean of 100 and a standard deviation of 15 points, okay? Which means that in my normal distribution of IQ, the average is 100, one standard deviation above and below would either be 115 or 85, two standard deviations above and below 130 and 70, and then at three standard deviations below is 55, and three standard deviations above 145, okay? Now, if I wanted to compare your IQ to the distribution of IQs to see how smart you are, this is the distribution I would use, okay? However, if I want to compare a sample to a distribution, this is no longer an appropriate distribution because I'm looking at the mean of an entire sample, okay? Unless I get that sample from the Dawn of Hope, that mean is not going to fall down here, okay? Unless I get that sample from Mensa, that mean is not going to fall up here. And so in a distribution of means, there's going to be a whole lot less variance. There's no way I would get an average if I just take a random sample in the population that I would even get an average of 115 or 85. It's very unlikely. More likely what it would be if I take a mean from this population, I might get a mean, or a sample, I might get a mean of 103. And if I take another sample, I might get a mean of 101. And if I take another sample, I might get a mean of 97. If I take a sample from Tennessee, I'm liable to get a mean of 95. If I take a sample, just randomly from the college, might be 105. But you can see that the means have a very small range, okay? Not nearly the range of what that we would find in a distribution of individual scores. So instead, we are basing our comparisons on the distribution of means. So if I were to continually select a sample from this population and calculate a mean, and then set these means up in their own distribution, they're going to have much less variance than the distribution of the individual scores. As a matter of fact, the distribution of means has a couple of unique properties, and you should remember these from Prob and Stats, okay? But it's called the central limit theorem, and that says that the mean for the sampling distribution of means is going to be equal to the mean in the population. So basically, if I do this a bunch of times, the means for these samples will end up leveling out to be the exact mean in the population, okay? But we can already see here that the standard deviation is going to be much smaller. 95 to 105 is my range here with a mean of 100. So it's a much smaller range. So the standard deviation for the distribution of means is going to be equal to the standard deviation for the population divided by the square root of n, okay? Now, the reason we divide by the square root of n is, let's just say, the bigger my n gets, the closer my sample is going to be to the actual population mean. So if my n is just 25, then I might have a sample with an IQ of 90, or I might have a sample of an IQ with 110, okay? Because my sample's pretty small. But if my N is getting up to be 100, then it's going to be a whole lot more likely that this sample is going to be reflective of the population. And so with an N of 100, I might get a mean of 98 and a mean of 102, but I'm not going to have as big a range as I would get when my sample is just 25, okay? So let's use this IQ data here. If indeed the standard deviation for the population is 15 and my N is 25, then the standard error of the mean, the standard deviation for this distribution, we call the standard error of the mean, will be equal to 15 divided by the square root of N, 25. So 15 divided by 5 is going to be 3, okay? Now notice though, when my sample is 100, that's going to be even smaller because my distribution is going to scrunch up even more, because that sample of 100 is going to be more like the population and come closer to that mean of 100. So the sampling distribution, or the standard error of the mean for that distribution, would be the mean for the population divided by the square root of N, which in this case is 100. And now all of a sudden the standard error of the mean is just 1.5, okay? So this is the test that we would use when we are comparing a single sample mean to population that still has known values for mu and sigma, okay? And actually the example that I'm using for the in-class example video is based on this data for IQ, okay? So let me erase this board and we will do that particular statistical test. So our research question here is, are the IQs of students at ETSU higher than the general population? A researcher takes a sample of 25 students and determines their average IQ is 112. Is this significantly higher than the known population mean of 100 with a standard deviation of 15 at a significance level of 0.05, okay? So coming here to the board, let's go ahead and get out the important information out of that question. First off, we know that our sample is 25 students, okay? We also know that that sample has a mean of 112. We also know that the population has a mean of 100 and a standard deviation of 15 points, okay? Also, we are setting that alpha level at 0.05, and we're going to use our z-score for a single sample, not a single person, but a single sample to test this hypothesis, okay? So step 1 of hypothesis testing, what is our hypothesis? What are we testing? Well, it tells us here, we want to know, is the average IQ of ETSU students significantly higher than the known population value, okay? So here in our hypothesis, we're not comparing X, a single score, to mu, the known population mean. We are comparing the sample mean to mu, the known population mean, okay? And so our null would then again be no, it's less than or equal to mu. Okay, step 2, we've got to determine our critical value, and I'm still using the z-score distribution because I know my population parameters. As long as I know both mu and sigma, I can use a z-score distribution, okay? And 0.05 is our cutoff, and it is on the upper end because we've got a greater than sign. So it's going to be the exact same value it was in the last problem, which was 1.65. So Z, critical value to reject the null, is 1.65. We've got to be greater than that in order to reject the null. More extreme, okay? And that is always the key. Whatever that number is, we've got to be more extreme. So if that was a negative 1.65, we'd actually have to be less than, more extreme than the critical value, okay? The third step is to calculate the hypothesis, or calculate the statistic. Now the Z-test for a single sample is equal to the mean for our sample minus the mean for the population divided by the standard deviation for the population divided by the square root of n, because we have to have the standard error of the mean, okay, for our distribution, as opposed to just the distribution for the standard deviation for the population. All right. So Z here is going to be equal to our mean of 112 minus the population mean of 100 divided by standard deviation of 15, which is further divided by the square root of 25. So I end up with 112 minus 100 divided by 15 divided by 5. So 12 divided by 3 is going to be 4, okay? So our Z-score that we calculated is 4. It is indeed greater, more extreme than, it would probably actually fall up here somewhere, than our critical value of 1.65. So again, in step 4 here, we are going to reject at ho, okay? 4 is greater than 1.65. Now, there's a kind of a little trick here, a clincher here though. If this sample size gets big enough, I could make a 1 or 2 point difference appear to be significant, even though it isn't, okay? So let me just kind of show you that. Let's just say my sample of ETSU students only had a mean of 102, and I'm comparing them to the population mean of 100. We wouldn't expect that to be a significant difference, okay? But let's say for my sample of ETSU students, I don't just have a sample of 25, but instead I have a sample of 225. Is that 15 squared? Okay. So now 102 minus 100 divided by 15, oh sorry, it's the square root of that 225. 15 divided by 15, now I've got 2 divided by 1, which is 2, which is still enough for me to reject the null, okay? It's still greater than 1.65. But the only reason I'm rejecting the null here is not because there was a significant difference between our groups, but because of the fact our sample size was so large. So now the APA requires, whenever we do a statistical test in which n is part of the formula, we have to follow that up with what is called an effect size statistic, okay? In an effect size statistic, we basically make a comparison between the two means, 102 and 100. But we divide them by the original standard deviation for the population, not the sampling the distribution of the mean. So we are going to divide it by 15. And 2 divided by 15 is going to give us a very small value, okay? And let's see what that value is. It's going to be 0.13, okay? And we can see here on the slide related to the effect size that anything below a 0.2 is considered a non-effect, okay? Small effects are 0.2 to 0.49, medium effects are 0.5 to 0.79, and large effects are 0.8 and larger, okay? So coming back over here, we've got this 0.13. That would indicate to us that there really is no effect of being an ETSU student on IQ, okay? Now let's look at the data in our original problem. The D for that would be the 112 divided by 100, or I'm sorry, minus 100, divided by 15. Just the standard deviation for the population, okay? Sigma. And so that is going to give us 12 divided by 15, which is 0.8. And yes, we have a large effect, okay? But this is important to do, this effect size statistic, whenever we are using a formula that includes n as part of the equation. And we're going to see throughout that most of these equations do incorporate n in the formula, and thus effect size statistics have to be calculated for all of our statistical tests just to back up our data and significant effects that we find, okay? Alrighty then. Now the next test we are going to do is going to be a single sample t-test. When I don't know both mu and sigma, I can't do a z-test, okay? If I just know mu, but I don't know sigma, instead I have to estimate sigma using the data from my sample. And when I estimate sigma using the data from my sample, I generally underestimate because of the fact there's always going to generally be more variation in a population than there would be in a single sample of people, okay? No matter how diverse that sample is. So again, dealing with that IQ data that we're looking at here, in the whole population, people's IQs range from 55 to 145. But it's rare, well, even more than that, okay? But between the -3 and +3 standard deviations from 55 to 145. And in all true reality, in the population, people's IQs vary from 20 to, 200 plus. So there's a lot of variance in the population, okay? Now, what is the chance? These are really rare scores, 55 and 145. So what is the chance if I were to take a random sample of 50 people, I'm going to end up with somebody with an IQ of 55? Not very good. If I, take a random sample of 50 people, the chances I end up with somebody with an IQ of 145, really small, okay? So in a sample, I'm not ever going to have quite as much variance as I do in the population. And so if I'm using my standard deviation in my sample to estimate what my standard deviation for my population is, it's going to be what we call a biased estimate. And it is going to underestimate what this value is, okay? So instead, we adjust that. And we actually calculate an unbiased estimate of the standard deviation. And instead of using the same formula, so for the SD, the formula we used in the last chapter was the sum of every score in a data set minus the mean squared divided by n and the square root of that, okay? Here we want to make this a slightly bigger value, so it is an unbiased estimate of the population value, okay? So S is going to be the square root of the sum of the squared deviations, same as here, every score in the data set minus the mean squared, divided by n minus 1, okay? And that n minus 1 makes this number slightly smaller in the denominator, which makes the overall value slightly larger. And that corrects for the fact that the sample standard deviation will be a misrepresentation of the population standard deviation, okay? However, we're not done here because we are still comparing, this is still for a population of individuals, and I'm comparing a mean to a population of means. So I still need to make this the standard error of the mean, and I would do it the same way by taking this S value here, which was our unbiased estimate of sigma. So S, we would say, is roughly congruent to sigma, all right? And we're going to take this S value that we calculate here and again divide it by the square root of n, just like we did here in our single sample z-score, okay? So let me erase this board and we will do the t-test for a single sample, okay? our in-class problem for a t-test for a single sample is that the mayor of a small city wants to reduce the amount of litter on the roadways. He implements a citywide campaign to reduce the amount of litter, including televised ads promoting education regarding the impact of litter and heftier fines for litter offenses. The average number of bags of trash picked up each month on each mile of roadway is 18. After the program implementation, the number of bags picked up per mile was measured on 16 randomly selected miles, and the data was as follows, and there is our data for the 16 randomly selected miles. Did the mayor's program significantly reduce the amount of litter at a 0.05 level of significance? Okay, now here, our problem doesn't give us as much information. It gives us sample data, okay? So we know that the mean for the population is 18, but we don't know what sigma is. So because we don't know what sigma is, we're going to have to estimate it using this sample data here, okay? And we'll do it just like I demonstrated a minute ago on the board. The only other thing that our problem tells us is our alpha is 0.05. And it also clues us in as to what we should see in our hypothesis. And again, I am just like on the z-test for a single sample. I'm comparing a single sample's mean to a known population value of mu. Okay? And the mayor thinks that mean will be less than mu because his program is going to reduce the amount of litter. So that is what our hypothesis is going to state. Whereas the null would say, no, it'll either be greater than, people get mad at the commercials and just chuck their trash out the window because they're pissed off, or it won't make a difference whatsoever, okay? So step 2 for our test is to determine the z critical value, okay? Now we're still dealing with an alpha of 0.05 here. And it is a one-tailed test, but this time I'm on the lower end because I have a negative sign in my hypothesis, or a less than sign. So as far as my z critical value is concerned, my 0.05 region for rejecting the null shifts to the lower end of the distribution. Okay, and now my 5% is down here. And my z critical value is still going to be the same value of 1.65, but now it is the negative value of that z-score. And so my critical value would actually have to be less than my calculated value would have to be less than, more extreme than, 1.65 in order to reject the null. Negative 1.65, okay? So we're not quite ready to do step 3, because first of all, we need to know what the mean is for this sample, and we need to know what the standard error of the mean is, okay? And there are a couple of different steps that we have to do to get to the standard error of the mean, okay? So first, we want to calculate the unbiased estimate of that mean, or the standard error, which is going to be equal to, again, the sum of all of our deviation scores squared, sum of squares, divided by n minus 1, okay? And then I have to change that value to the standard error of the mean by taking whatever I get there and dividing by the square root of n, okay? So let's do this process. And to calculate my mean and to calculate my sum of squares, I am going to use Excel. Because why in the hell would I do all of that tedious math of subtracting each of them, creating each of the deviation scores and squaring them all by hand if I didn't have to? I wouldn't, so I'm not going to. So I'm going to go to my Excel sheet and I'm going to put in the bags per mile, the data that was listed in my problem, okay? And then I'm going to calculate my mean. First thing I got to do is add all of my sums up. I don't know why it's doing that.
It's because you selected the top cell as well.
Okay, well, shoot. So I'll just tell, I wanted to add these numbers. Normally it's very intuitive and just does that. Sum Okay, there we go. There it's working correctly. And it just adds that up. The sum of x is 211, so the mean for x is going to be 211 divided by 16, because we have 16 pieces of data. So the average number of bags per mile that was picked up on the roadways after the mayor's program was implemented was 13.1875, okay? 13.1875. All right, now let's calculate our sum of squares. And I'm going to do that using Excel. And for every piece of data I have here, and I'll go ahead and delete that so it doesn't confuse me, I'm going to subtract 13.175, okay?
1875.
1875. All right? And I'm going to do that for every piece of data. I want it to equal this number minus 13.1875. And again, very important that you type that mean in just like that in order for it to work correctly and for you to be able to copy and paste that down. Once I've done that in one cell, I didn't need to do it for two, I just did it for you, I can copy that down to all of the other cells. And it is going to automatically subtract the mean of 13.1875 from every piece of data I have. The next thing I want to do is square all of those values. And once I've squared all of them, I'm going to add them up. And that is the sum of squares value that is the numerator for our initial formula over here. So let's move that to the board, 278.4375. All right? All righty then. So now we're ready to come over here and at least find out what the standard error of the mean is, okay? So here we go. Our unbiased estimate of the population standard deviation is going to be equal to our sum of squares, 278.4375. Not quite sure why I put that point there. Divided by n minus 1. Our n was 16, okay? And I guess I should have put that over here in our original information in the problem. N is 16. So divided by 16 minus 1. Okay? Now I'm going to have to go use a calculator to calculate this, okay? But let's come over here and do that. So I'm going to bring up my calculator. And I'm going to take 278.4375 and divide by 15. Okay? And it gives me a value of 18.5625. All right, I still need the square root of that in order to have the unbiased estimate of just the standard deviation. So the square root of 18.5625 is 4.3084. Okay? Now I'm still not done. That is the unbiased estimate of the standard deviation. I still need the standard error of the mean, and that is going to equal this value I got here, 4.3084, divided by the square root of n, 16. So I end up with 4.3084 divided by 4. That's going to give me 1 point something. Let's find out exactly what that point something is. $1.0771. All right, and that is this, the denominator for our formula. So a t-test for a single sample is equal to the mean for the sample minus the mean for the population divided by the unbiased estimate of the standard error of the mean, which is what we just have calculated in those two steps, okay? So our t-value for step 3 is going to be equal to 13.1875 minus the mean in the population, which is 18, divided by the standard error of the mean, 1.0771, okay? So I end up with negative 4.8125. Pretty sure that's correct. Divided by 1.0771. And let's go over here to the calculator and see what that value is, okay? Sorry, help me out, Alex, my video cameraman. What are my numbers off the board?
Negative 4.8125 divided by 1.0771.
And I get a value of negative 4.468. Okay, that is more extreme. So my step 4, try my little distribution if I need to. My critical value is a negative 1.65. My negative 4.468 is less than that. It is way more extreme than the negative 1.65. So again, we would reject the whole, okay? Again, though, n is a part of this formula. And because of that, I have to calculate my D effect size, which is going to be the mean for my sample minus the mean for my population divided by my unbiased estimate of sigma, which is not S sub m, the unbiased estimate of the standard error of the mean, but it is just S, the unbiased estimate of sigma, which we calculated to be 4.3084. Okay? And then that is going to give us, and it's an absolute value, so it doesn't matter that this is negative. We'll just make that a positive number. 4.8125 divided by 4.3084 is going to give me 1 point something, okay? And I'm not going to walk back over to the calculator to calculate that because I know you guys can do that. And based on that, we know automatically it's greater than the 0.8, so we have a large effect, okay? Now there's one more little piece of a single sample t-test that we do, and it's called a confidence interval. You know, we're using sample data to estimate population values at this point in our statistics. And our sample data isn't always a perfect estimation, okay? So basically we want to say, well, the sample mean we got is 13.1875. But to what extent is that a real value? You know, to what extent is that the correct value? And y'all, I have made a big mistake here that I just realized that I'm going to go ahead and correct without it doing a different video. But walk back down here with me for a minute, Alex. I'm doing a t-test. I can't use the z-score cutoff. I got to use the t-distribution. So I've got to go to the t-chart that's on page 633 of my book, okay? I can't believe I did that. And I went all the way through it with that, but it doesn't change much. So we'll just change this right here, okay, really quick, and I apologize for any confusion that may have created for you. But it is a t critical value that we are looking for, okay? It works the same way. We're still 0.05, we're still one-tailed, we're still on the lower end. So whatever our value says here, we're going to we're going to make it a negative number, okay? The t-chart, though, based on your notes, is determined by the degrees of freedom. Degrees of freedom being n-1. So we're going to follow our chart down to the number 15 on the side, n-1. I'm going to look at proportion in one tail of equal to 0.05 that goes across the top. And I'm going to see that value for T, the critical value instead, was not 1.65, it was negative 1.753. Okay? Everything else is the same. I still reject the null, okay? But sorry about that, 1.753, okay? Now here on the confidence intervals, what we want to do is use this T-chart to determine the range of values that 95% of additional sample means would fall in, okay? So my sample value is 13.1875. To determine the 95% confidence interval, I'm going to look for 5% two-tailed in both tails. So that means I've got 2.5% up here and 2.5% down here. And I want to determine the values that correspond to that spot, okay? So basically what I want to do for my confidence interval, so CI 95 is how you would write that, 95% confidence interval, is going to be equal to the mean that I established for my sample plus n minus the T value that corresponds to this point for two-tailed test, 2.5 in each tail. So we'll look at the chart and get that here in just a minute. Divided by the unbiased estimate of the standard error of the mean, which is, or multiplied by the unbiased estimate of the standard error of the mean, which is 1.0771. Okay, so I need to go to my T-chart, and instead of looking at 0.05 one tail, I'm going to look at 0.05 two tails, and 15 degrees of freedom, and I'm going to find that that value is 2.131. You got your phone in your pocket, Alex?
Mm-hmm.
Could you handle that and multiply 2.131 times 1.0771 all at the same time?
Multiply?
Yeah, multitasking here. He's holding a video camera and using his calculator to find out what that is so we don't have to go all the way back down there to figure it out.
$2.2953.
2.2953. Okay, and add that to 13.1875.
$15.4828.
And subtract that from 13.1875.
Oop. Hold on. $10.8921 or 8922.
Okay.
10.8922.
Okay. Y'all, the way we would interpret this is one of two ways. You could say that you would anticipate that 95% of additional sample means would fall between 2.899. So if we go another 16 mile of roadway, we would expect the bags to be somewhere between 10.89 and 15.48, okay? We can also say that we are 95% confident that the true mean falls between those two values, okay? All right, that concludes our video example for hypothesis testing. Please, I encourage you to review this, to look at the homework example documents that fall directly below this video that show you what your homework would look like if these problems that we just did on the board were your homework problems. And also, I encourage you to come see me. If you are struggling with this, I know statistics isn't the easiest thing for some people to get. online and in just a video like this. So if you find you're having trouble with this part of the assignment, please utilize my office hours and come see me here on campus, okay?
I'm going to get the view of the board.
All right. And Alex is going to take a scan of the whole board real quickly, and that will conclude this video. Y'all have a great day and have fun doing math.